Hey guys, my name is Sandesh, and this is our project for Professor Knospe's Intro to Automatic Controls class. So we have a self-balancing inverted pendulum, and as you can see, for our system, our actuators are these two motors with propellers on them, and then our controller is this Raspberry Pi, and our Raspberry Pi sends PWM signals to two of our H bridges, which then apply the corresponding voltage to these to the motors. And as for our sensor, we have a IMU 6050. It's a gyroscope and accelerometer, and so that is a data. So that senses how much this contraption is tilting, and that way we can process that data and correspondingly apply enough thrust to keep this thing balanced. And as you can see, this propeller is used to provide thrust in this direction, and this is to provide thrust in this direction. So if we apply a little bit of input force impulse into it, then this top motor acts up and then it brings it back, and if it's the other way, this bottom motor acts up and it kicks it back up. And as for our algorithm to keep it balanced, so what we have is we have the accelerometer, which we use to determine how much it's tilted, and that's just some trigonometry, and that's what we use to determine how much the angle which it's tilting at any given time. And then we also use the gyroscope data to then figure out how quickly it's moving, how quickly the theta of this is tilting. So right now, this contraption, its theta is at 0, and that's our set point, and that's what we're trying to balance about. And what happens is if we tilt it a little bit, the theta changes, and it also has a certain velocity. So our controller takes that and then applies corresponding derivative and proportional gain to the top motor and subtracts from the bottom motor in order to bring this contraption back up like that. When it's tilted like this, it brings it back up like this. So it's very similar to how how a magnetic bearing works, where you apply a nominal thrust to each one of these in order to keep it balanced under ideal conditions. So the net torque of this system will be 0. And then if you have it kind of, error of theta on one side, you decrease the thrust on the bottom actuator and you increase the thrust on the top actuator. And so that's how our controller is designed. One of the biggest problems that we had with our sensor is that it picked up a lot of vibration from the motor, since these motors and the propellers are not properly balanced, and that vibration went into our accelerometer data, and so that's why we had a lot of noise. So in order to clean up the data, we applied a moving average, and that adds a slight delay, but however, it does clean up the data significantly. And another thing we did was we did a fast Fourier transform of our accelerometer data in order to find out what frequency the noise was at. And then after we did that, we kind of used the internal filter that the accelerometer has. So we set the bandwidth of this to be less than the frequency of the noise, which would be okay for our design. And the other thing we did was we added some foam in order to dampen the vibrations, and that helped a little bit as well. And then additionally, so what we realized during the design was that, during the implementation was, the gyroscope data is a lot cleaner than our accelerometer data under these vibrations. So for our derivative term, we used the gyroscope data for the velocity, at which it's traveling, and then so that also significantly helped our final controller implementation and the stability of this.
Walk. Tilted. Let go. Stabilize, hit it.
Next stabilize.
Just hit it. Hit it on the other side.
Come on, fight.